Okay, here we go. We are going to analyze graphs of functions and piecewise. Remember piecewise from last year?
Piecewise.
Okay, so they're coming back a little bit. Our objectives: test for symmetry, identify even and odd functions. We're going to graph piecewise-defined functions, investigate increasing, decreasing, and constant behavior of a function, and then this is something that should sound familiar. Determine relative maxima and minima of a function. Okay, so again, it's not like an absolute max or min that a function has. It's like somewhere in the middle of the end behaviors. Like what is the largest and smallest? Okay, look at A, B, and C real quick, and you don't have to write this down. But for A, if I asked what type of symmetry does that graph have, what would you say? What type of symmetry does it have? Yeah.
Horizontal symmetry?
Okay.
The one side on the first quadrant is the symmetrical side.
Okay. What would it be? This direction? Horizontal?
Well, the line down the middle,
Okay.
vertical line. The two pieces are horizontally symmetrical, but they're,
From
they're
here to here.
mirrored along a vertical line.
Okay, so this vertical line, if I were to reflect it, would this be symmetric across the y-axis? Does that make
Yes.
sense? Okay.
Exactly.
What would B symmetry would be? X-axis, right? Now this one is really, I don't know if you've heard of it too much. If I take this piece, just this part of it, and rotate it like 180 degrees over here, would it fit on top of it?
Mhm.
Yeah, we call that symmetric around the origin, okay? And again, we're gonna talk about this in this lesson, but just to maybe start thinking about it, okay? Alrighty. It's like WD-40 on those. It's getting harder to push that back. Okay, let's talk about symmetry first. So let's test for symmetry. Okay, so let's consider an equation and variables x and y. Okay. Now I'm going to have, so these three that we did in the warm-up, I'm going to go ahead and define it for us officially. The graph of the equation is symmetric with respect to the y-axis if substituting negative x for x in the equation results in an equivalent equation. We're going to do an example, so if the definition's like, I kind of understand what it's saying, we'll have some more concrete with it. So it's a y-axis. So if you look at the parabola we did over here, okay, if x is 1, my output's 1. If my x is negative 1, my output's still 1. It didn't change it, right? Didn't change it at all, so therefore, y-axis symmetry. Okay. And by the way, I'm just changing a couple things. I'm going to rewrite the same explanation, just changing y-axis and what we're substituting. The graph of the equation is symmetric with respect to the x-axis if substituting negative y for y in the equation results in an equation, well, in an equivalent equation. Okay. So that would be B's graph, right? Okay. If I were to plug negative y into the equation, okay, then the output's going to be positive y, right? It's still the same x value. So now we have to talk about the origin. Now the origin is going to combine these two properties here for symmetry. So here's the last one. Okay. The graph of the equation is symmetric with respect to the origin. Underline that. Okay, if substituting negative x for x and negative y for y in the equation will result in an equivalent equation. Okay? And that's what part C. So if you want to, guys, if you want to, next to each test, you could put, if you want to put one of these graphs next to it, that way you can see what it looks like. But if you look at the graph for C, if I were to plot a point like 1, 1, well, if I take the opposite of both, okay, I get it on the other side there. That's a property of origin symmetry there. Okay. Here we go. Determine whether the graph is symmetric with respect to the y-axis, x-axis, or origin. There's my two graphs. And again, we're just going to go ahead and use the test for symmetry properties over there and figure out what we're looking at. Okay. So for part A, what would you say? What type of symmetry are we seeing in part A? X? Honestly, not your question. Yeah, it's x-axis, right? If I reflect this across the x-axis, is it going to match up perfectly? Absolutely, right? Okay. So here's what I want to do, and I don't know if I'm going to have enough space. Should I chance it? Well, let's see. I'm going to show you algebraically how to do this as well, okay? So for instance, if you look at the graph and you're like, I mean, this is pretty obvious, but how do we show it algebraically? So if we're going to test for x-axis symmetry, plug negative y in for y, okay? So there's my original equation. So I have x equals absolute value of negative y. Now you want to simplify it too. So you get x is equal to, one of the properties I've shown you when we did absolute value about a couple weeks ago, is that you can split up any sort of multiplication there, and it's still equivalent. So the absolute value of negative 1 is 1, so we get this guy. So x is equal to the absolute value of y. That makes us happy. Okay, so this is an x-axis reflection. So visually we can see it, but also algebraically we can prove it as well. Okay. Now let's take a look at part B. What type of symmetry do you think that guy's going to have? Origin. Does that make sense? Again, think of origin as rotating it like 180 degrees. So if you take this, rotate it once, rotate it twice, it's over here. See, this is the origin. So let's go ahead. I'm going to put the work underneath it just to show algebraically that it is. Because again, if you're not sure, you can at least prove it. So that's where we're going to plug negative x in for x, negative y for y, and we should get the same equation, right? That's the hope. And if we do, we're good to go. Okay? So let's do that. So for this one, okay, we're going to have negative y equals the cubic root of negative x. And when we simplify it, we should get the original, which means origin symmetry. Okay, so we have negative y. That is not a y. Don't even know what that letter was. Okay, negative y equals. Now, same thing with roots properties. I can split this apart to the cubic root of negative 1 times the cubic root of x. Okay? There's nothing wrong with that. That's a property that we use with roots. Okay? So looking at this, we get negative y equals the cubic root of negative 1, which is negative 1, times the cubic root of x. And then I could divide a negative 1 to both sides, so we get y is equal to the cubic root of x. All right. So yeah, this has origin symmetry. Okay. So any questions of how to look at that graphically and then just algebraically? Not too bad, right? Okay. All right, let's try a different example. Let's try a hyperbola. Same instructions. Determine whether the graph is symmetric. With respect y-axis, x-axis, or origin. Let's look at one of these. I'll show you what the graph looks like afterwards, but right now, let's say you were given that. Okay, so what should we do?
Multiply everything by 16 is what I do.
Get it to where it's just something that's easy to work with? Not a bad idea. Considering I'm only plugging in negative x and negative y, I don't think I have to do that this time. Okay? But again, I don't want to disprove that. So what I'm going to do here is I'm going to test all of these. So x-axis, let's go ahead and figure out if it works for the x-axis. So here we go. So x squared over 16 minus negative y squared over 4 equals 9. Well, that looks pretty good to me, huh? This results in x squared over 16 minus y squared over 4, because negative squared gets rid of it, equals 9. Hey, we're good. It's x-axis symmetry. But that's not all. There's more. Let's try y-axis. So negative x for x, right? Yes?
If the negative square makes it positive, why is it positive square still? Wouldn't that take the square root?
No, you're just squaring this number. Well, this variable, I should say.
You're not, oh, yeah, okay, no, never
I'm
mind.
not solving it. I'm not like
Yes.
doing the opposite. No, nothing like that. Okay, so this one, negative x squared over 16 minus y squared over 4 equals 9. And you can see that, hey, this can become positive. It results in the same equation. So, hey, it's respected, or I can't talk. It's symmetric with respect to the y-axis. But there's more. If both of these worked, would it also be origin symmetry? I'm not going to write that part down. I think we're okay if I plug both of those in. We saw it already. So this, in particular, so this is symmetric to the y-axis, x-axis, and origin. So what's it look like? What is this mysterious thing? There you go.
What in the world?
If I rotate it 180, so it'd be 90, 180, so it works across the origin. If I reflect it over here and back over, we're good with that. If I reflect it across the x-axis, this comes down here, this comes down here, this comes up here. So therefore, it all works.
It's like a circle.
Just chop down the center and move the 2 places. But yeah, that's what it looks like. We'll talk about those more in like trig. Those will pop up a little bit more. Okay, so that was symmetry. So our next objective is even and odd functions. So first we got to figure out what are they. Let's define them. A function, which we'll just call f right now, is an even function if f of negative x equals f of x. For all x in the domain of f. Okay? Now, if that's the case, think about what this is saying. If I'm plugging in negative x in, I'm still getting the same equation. Okay? Well, wouldn't that be y-axis symmetry? That's what we just described. So I'm going to add a little note here. So the graph will be, no, b, not by, symmetric with respect to the y-axis. So I'm just taking the symmetry that we just defined and kind of including it in this definition, because that's what this is saying. Okay, this is saying if you plug negative x in, you'll still get the same thing as if you just plug normal x in the equation. They're going to come out equivalent to each other. Okay, so that's what that's stating right there. Now, let's talk about odd. A function f is an odd function if f of negative x equals negative f of x for all x in the domain of f. Okay, so that's what an odd function is. Well, let's think about that. This is saying if I plug in a negative x, I get a negative y. Well, isn't that what origin symmetry is, right? Negative x, negative y for an x and y. So I'm going to go ahead and include that in here. So therefore, we could say the graph will be symmetric with respect to the origin. Okay. So let's try some out. And here's what we're going to do. We're going to try it with a graph first and identify it. And then after the graph, I'm going to show you how to do it algebraically. By inspection, determine if the function is even, odd, or neither, which that can happen. Okay, so those are my graphs. They said just by inspection, is it even, odd, or neither? Okay, let's look at the even part. So if it's even, look at this note I made here. It's symmetric with the y-axis, right? Okay, so let's look at this guy. Is this symmetric with the y-axis? No, because if I bring this over here and this over there, it does not look like the same graph. So it's not even. Does that automatically mean it's odd? No, because it could be neither of those. So let's what odd say. is in respect to the origin. So if I take this and rotate it 180, so 1, 2, and then same thing here, 1, 2, I think I'm gonna get the same graph, huh? So this is symmetric to the origin, so therefore, well, let me write that out. The graph is symmetric to the origin. Therefore, it's an odd function. Okay. There we go. Okay, let's take a look at B. Again, let's start with the even part. Is it symmetric across the y-axis? No, because if I move this over here, it's still pointing in that direction. It's not the same graph, so it's not going to be symmetric that way. Origin, if I rotate this 180, so 1, that's 90, so 2 would be 180. I think we're getting the same thing as if I reflect across the y-axis there. That's not going to work. This would be a neither case, okay? So I'll just put here the graph is not symmetric to the y-axis or origin. Therefore, neither odd or even. Okay? Which again, that can happen. Let's try algebraically now. So by visual inspection, it's not too bad. But if you can't tell visually, we got to come up with an algebraic way of doing this to confirm it. Determine if the function is even, odd, or neither. Okay? So let's try this guy. Now again, could you use a graphing utility and test it yourself? Absolutely. But even if you couldn't do it by the graph, let's see how we can do this algebraically. Okay. So what I'm going to do first, and by the way, no reason. I could start with testing it if it's odd. Let's see if it's even. So this time I'm going to look at the very first part of my statement. If it is even, if I plug negative x in, I should get the same equation. That's what that's telling me. Okay? So let's just write that out. That way it's like a reminder, okay? That way we don't have to keep flipping back and forth between pages. So this is our goal. So f of negative x, let's plug negative x in. So we get 5 times negative x to the 4th plus 2 times the absolute value of negative x. Okay. This is actually already looking promising. If you're looking at this ahead of time, you're like, this is looking pretty good. If I'm raising this to even power, does that get rid of the negative? Yeah, right? So this is just 5x to the 4th. Treat that like a negative 1. Pretend there's a negative 1 in place. And then what would that give me? Okay, over here, I already did an example like this, but I'll write it out again. You could bring the negative 1 out, okay? Because again, if I multiply, I get the original. But this just gives me a 1. So I just get 5x to the 4th plus 2 times the absolute value of x. Is that the same thing I got up here? It is. All right. We're happy. So therefore, the function is even. Now, I don't have to check if it's odd. It can only be one or the other. Okay? The only time you can consider that is if all the points are just on the x-axis. So you're only looking at the x-axis, but that's really not much of a function that we use that much anyway. Okay? All right. So any questions on how to do that algebraically? That's all you're doing. Just plugging it in and see what happens. Okay, moving on. So we did symmetry, even and odd. Hey, we're on the piecewise functions. Those guys are fun to mess around with. I'm actually teaching my Algebra 2 students piecewise right now. So first, let's just interpret. So interpreting a piecewise defined function. Now I'm not going to go in full detail because we've done that already, but let's just recall some things here. Okay, so there it is. There's my piecewise. Instead of, just to kind of go through it, instead of me writing h of x equals this, h of x equals this, h of s equals this, I'm writing it only once and putting it, all three equations listed in a vertical column. And then what's on the other side, if you remember, these are our restrictions, okay? Those help us graph it because I only want to graph this equation as long as x is less than or equal to -1. I only want to graph this guy if it's between -1 and 2, and only graph this line if it's greater than or equal to 2, okay? So we're going to do an example of graphing after this. So let's find the following. Oops, not F, this is H. Okay, so those are the three we're going to try and figure out. Oh, it's H, not F. I'm so, it's like X being the most common variable. We're so used to writing it. F is the most common function name, so it's my brain's an autopilot. Now, to evaluate h of -1, we got to figure out where we put it, right? Can't put it in all of those. So look at your restrictions. Where is -1 allowed to go into, the first, second, or third equation? First, because there's an equal to symbol, right? So I'm going to plug -1 into here. So h of -1 equals the absolute value -1, which is 1. We're done. That's it. I don't plug it into the other ones because it's the domain of it's being restricted, right? It doesn't belong in those ones. Okay, next, h of 0. So which one of these does 0 belong into? This one, right?
Yeah.
Yeah, because 0 is between -1 and 2. So h of 0 is equal to 0 squared, and that's just 0. Gotta love 0. Okay, so if you're following the trend and pattern, h of 9 has to go with this guy, right? Because 9 is greater than or equal to 2. However, is there a variable here? Am I plugging that into anything? No. So my output, no matter what I plug in, is -4. Remember, this is a horizontal line, right? That goes through -4 on the y-axis. Okay. Questions on evaluating? Does that look familiar from last year? Okay, let's try graphing one. Pleasure. Okay. Let's do a grid of a 7x7. Okay, that's what I'm going to do. Let's do a grid of a 7x7. There we go. That'll be good enough for us. Well, how do we even start it? Easy. Get a new colored marker. That's your first step. All right, let's use red and green Be like Christmas colors. Okay. Well, look at your first function. This is like me saying y equals 2x plus 5. So let's graph the line y equals 2x plus 5. I'm going to use green for that one. So I'll put that next to it. So I'm going to start at 5. That's the y-intercept. 1, 2, 3, 4, 5. So I'm going to put a point there. And then what I'm going to do is, graph the full line, but only erase the things that I don't want. Okay? So the slope would be like up 2 to the right 1, down 2, left 1, and then again down 2, left 1. Did I do that 1? Yeah. Okay. And I can keep going. And let's do one more. Why not? Down 2, down 2, 1, 2, left 1. Okay, we'll do one more. So here's my points. Now, the line, I'm not going to draw the line, okay, would go infinitely left and right. But this is my restriction. I only want to graph the line when it's 0 or less than that on the x-axis. So here's 0. So where does it hit my line? Here. And I only want this stuff. That's it. Okay? So I'm going to keep this. This dot up here and any other dots above it, I don't want, because that's bigger than 0. Okay? So I'm going to go ahead and draw the line now. Just like that. So again, I'm not drawing this up here because I don't want it. I'm being very picky today. I don't want the full thing. Because there's an equal to symbol there, I could put a closed dot. I'm going to make it very big. That tells the reader that, hey, if you plug 0 in, it's going to be this part of the function it belongs to. Does that make sense? So now let's look at this guy. We can use transformations, which we've done in the past. This is going to shift it to the right 2. So over here we're 2. Okay. And I'm going to graph the full thing. So let's see. If I plug in, let's plug some points in just to make it accurate. If I plug 0 into here, that would give me a 4, right? So it's going to hit at this spot, which that can happen. Okay. Oh, no, wait, this spot. My apologies. So it's going to hit here, open dot, because I don't want to include it. So instead of me drawing the full thing, it's going to go down to here. Okay. And just bounce back up infinitely. So that one's actually even easier to draw. Because again, I'm not including 0, open dot, and then everything in the other direction. My transformation moves the vertex. So that's why I knew that that was the vertex. It wasn't just by random, like I thought, oh, that's the vertex, I'm going to do that. That's what the transformation does. Alrighty. What do you think? Look familiar? Hopefully, right? Hopefully it wasn't anything too new for you guys. Okay. Moving on. So there's one other piecewise that we have to talk about, and then we're on to the increase and decreasing. We're going to talk about step function. Okay. So here we go. We have a special category of a piecewise defined functions called step functions, which it's accurately named because it looks like steps when you're done. Okay. And one of the most important step functions I'm having a hard time writing. Is called the greatest integer function, or function. Don't you love it when there's multiple names for one thing? Math's good for that. So what's that look like? Here's the equation. Okay, it's double brackets. Okay, so that's where whatever we plug into here is the greatest integer less than or equal to x. Okay? So let me just give you like two little small examples underneath it. Okay. Let's say I plugged in negative 2.5 and 5.6. All right, so what's that going to look like? Well, remember, it's the greatest integer that's less than or equal to it, okay? So for this guy, that would be a negative 3, okay? Again, it's one of those things where you're kind of getting rid of the decimal place, you're rounding in a way, and in this case, you're pretty much rounding down, okay? So for negatives, it's going to go in the other direction with it. For this guy, 5.6, that's just going to be a 5, okay? Because again, this integer is the largest without going over this guy, okay? Now if I had something like this, well that's just 5, okay? You know, again, it's either equal to x or less than that. So this is great with decimals because it kind of gives you that rounding perspective. But there's no a 5 and above you round up, 5 and below you round down. It's just you're always rounding down. Okay? Does that make sense? All good? All right, only half the class is asleep. I think I'm okay. All right, perfect.
Is that double square brackets?
Double square brackets, yep.
I thought it was a square and a curly.
Nope, double square. Sometimes I will say, computer science, they'll do something like this for floor notation because it's floor. And there's also something called ceiling notation, which is, well, you would round everything up no matter what. So if it was 5.6, you'd make it 6 anyway. But that's for something more specific if you ever need it. Nothing that we have to worry about in this class. Okay, so let's just quickly graph this. So graph the function defined by this. Okay? And here's how I'm going to do it. I'm going to create a table to do this. That's the easiest way, okay? Just create a table and see what happens. Now you're probably thinking, why the heck did he pick some of those points? I'm picking points in between two values, if you get the pattern to it. That way we can see what the behavior's going on, okay? So again, instead of me putting -2, -1, 0, 1, 2, I put a value just randomly. Just put any random number in there. I'm going to plug it into here and see what I get, okay? So if I plug 2 into here, I get -1. Now, what is -1 inside of here? Just -1, okay? That's the greatest integer that's less than or equal to it. It is that. Okay, next, if I plug this, -1.7, I get -0.7. So what's the greatest integer function put into that? It gives you -1. If I plug -1 in, I get 0. Okay, take the function to it, you get 0. And what I mean, I want to make sure you understand. What I'm doing is I'm plugging this in, simplifying it, and then I'm taking this afterwards to get to this guy. I'm just not writing the symbol each time. Does that make sense what I'm doing there? Okay. So if I plug in -0.3 into there, I get 0.7. And 0.7 with the brackets there is going to give me a 0. If I plug in 0, I get 1, so I get 1. 0.7 is 1.7, which gives me 2. If I plug 1 in, I get 2, which gives me 2. 1.5 gives me 2.5, which gives me 2. If I plug 2 in, I get 3, which gives me 3. And 2.4 gives me 3.4, which is 3. Okay? So again, I'm plugging -2 into here, I get -1. Take the brackets, that gives me -1. these are my final answers, this last column. Now notice, this is the reason why I picked a value in between. See how it's still giving me the same value, even though it's between these two right here? Okay, that's what all of these are telling me. Am I missing? 0, 1, 1, 0.7. Oh, this is 1. I say, wait a minute, that looked weird. That's what you get for copying too fast off your paper. Okay, so yeah, no matter what I pick in between those values, I'm getting the same output. So how does that look like graphically? Okay. Okay, I just did a 4x4 grid. So if you look at the first one, okay, if I were to plug in, oops, -2 is first, okay? So from -2 all the way to -1, my output's always -1, right? This whole direction. But as soon as I hit -1, which is this guy, my output's 0. From there all the way to the x value of 0. So that's why there's an open dot there, okay? And then continue the pattern with that. So this is a closed dot, open, closed dot, open. I think I stopped at 2, right? Yeah. So then closed dot, open for the last part. There we go. Okay. But yeah, there's a stepwise function.
Can you like explain that again, but like face this way?
Sorry.
It's okay.
So, for instance, if I look at this guy, from -2 all the way to -1, but not including it, the output's always -1, right? So that's what this is saying here. So from -2 all the way to -1, you're always going to get -1 output.
Okay.
But the open dot's here because as soon as I hit -1,
0.
now it's 0. So I got to continue with this direction. And then just follow the same pattern all the way through. It doesn't change. Okay. Alrighty, guys. So now we got to talk about. Well, am I going to be able to fit that? Yeah, I should be able to fit that. We'll be good. All right, let's talk about increasing, decreasing. Suppose that I is an interval contained within the domain of a function f. Now I'm going to draw 3 graphs for you to explain this. Okay, so it's 3 generic graphs. Obviously, we could tell which one's increasing, decreasing, and constant, but I want to put it mathematically to you. How do we write that? Okay? That's what the important thing is. Okay? And of course, the interval from x1 to x2, that's what I is for us. So we do the same thing for the other graphs, and then I'll put a description underneath it. Okay. So 3 different styles of graphs there. One that's showing an increasing, one that's showing a decreasing interval, and one that's, oh, forgot the I there, and one that's showing a constant interval. Okay, and again, visually we could see that. I don't think that's something that we don't understand. So how do we write this mathematically? So what we could say for the first graph is for all x1 that's less than x2. Okay, so again, all these values here, not including x2, but all these guys here, we can see that it's increasing, right? That our y values are going to be increasing there. So on that interval, f of x1 is going to be less than f of x2. Okay? So every output here for each corresponding x term is going to be less than this y term right here. Okay, so that's how we're defining an increasing interval. Now, decreasing is going to be the opposite. Okay? So for all x1 less than x2 on our interval, f of x1 is going to be greater than f of x2. Okay? So again, go in the opposite direction. So looking at this guy, okay, all these x terms, from here all the way over, every y term, or every y value, okay, is going to be less than f of x of 1. So this is going to be a lot larger each and every time than f of x2. And the constant, well, for all x1 less than x2 on our interval, they're the same. The outputs don't change. Okay? So let me put underneath what each one is and I'll step back. So increasing, decreasing, and constant. Okay? Just a little example of each. So I got one example to go with it. Use interval notation to write the intervals over which f is increasing, decreasing, and constant. Okay? So let's see here. This is going to be 1, 2, 3, 4, 1. Okay. There we go. Let me sharpen that point a little bit more. Okay. And again, we want the intervals that it's increasing and decreasing. Visually we can see that, right? When we're looking at this, visually we can see where it's increasing and decreasing. We're just going to figure out what x values specifically and putting an interval notation. Okay? We'll use a different color. We'll use red. Okay, the increasing part. Do we agree that that would be this guy right here? Right? Okay, so what x values do we see that? It's going to be from -1 to 1. Okay, is where we see that. So from -1 to 1 is where we see the function increasing. Now, I'm not putting brackets. The reason why I'm not putting brackets is I don't know what the function is doing at this specific spot. Is it increasing? Is it decreasing? I have no idea. But the values beyond it, I can actually use what I defined over there as saying, oh, it must be increasing. Okay, but again, no brackets when it comes to this stuff here. So where is it going to be decreasing? Okay, we have two spots, right? We have this spot where it's decreasing and this spot. So this is going to be one of those union intervals that we're going to be looking at here. Okay, so it's going to be decreasing from -2 to -1. That's the first little decrease. Union, okay, well, it's going to be what? After 1, it's just going to continue to decrease infinitely. So it's going to be 1 and infinity. So that's where the function's decreasing. And then constant, where it doesn't change, that's this guy right here. Okay? So for me, that's what? From -3 to -2? Okay? So from -3 to -2, it's staying constant here. It hasn't changed. None of my y values are larger or less than the other y value. Okay? All right. we got one last thing, one last objective. So now let's talk about relative maxima and minima. Okay, I'm gonna draw a picture to show this. But it would be nice if I had a title, so let me put the title up first. Now we did talk about this in Algebra 2. So this should look relatively familiar for you. Okay, so let's say I had a function that looked like that. And I want to talk about what's maximum and minimum. So look at what's happening. This function is going to increase indefinitely, right? It's not going to go anywhere. Or it is going somewhere. But it's not going to dip anymore. Like, it's done. It's going to keep going this direction. So there's not going to be a true maximum. Okay? Same thing here. This function is going to continue to go negatively in this direction, so there's not like a true minimum. But in between these end behaviors, there is a maximum min y value, right? We do know that. Okay? And visually we could see that this guy here is the largest y value that's left and right of it. So we'll call this one the relative max. Now, if we had more than one max, we call it maxima, that's the plural. And then down here is the lowest left and right of it, okay? So this is gonna be called a relative minima, okay? Does that make sense? So it's, okay, visually we could see that. We're just talking about what's in between the two end behaviors. What's the largest and smallest that we could see, okay? All right. So let's go ahead and just define it, and then we'll do the example. Definition. So f of a is a, I'll put R for relative, maximum of f if there exists an open interval containing a such that f of a is greater than or equal to f of x for all x in the interval. Okay, so if you look at that relative max point over there, that's what this is telling me. Okay, that this guy right here, this a term, this a coordinate, okay, whatever this a value is larger than all the f of x values left and right of it. Okay, that's how we know. And then we're going to define the same thing with minimum. So f of b is a r minimum of f if there exists an open interval containing b such that f of b less than or equal to f of x for all x in the interval. Okay? So it's the same premise, but I'm just flipping the sign. And I didn't use A again, I used B. That one we're not using the same letter, and it gets confusing. So if I look at the graph over here, okay, that's the lowest point. Whatever this B is on the x-axis, okay, the f values are not going to go any lower than that, left and right of it. That is the smallest. Just for that interval, because again, it goes infinitely in this direction, so it doesn't mean that's the lowest value. It's just it is for that interval. Okay? All right. So let's do this example to finish it. For the graph, y equals f of x shown. A, determine 3, determine relative min. And here's what I'm going to do to make it easier for you guys. Okay, I'm going to put the coordinates, these critical points. Okay, that way you can see it. Okay, so there's what the function looks like. So this particular spot is -3, 3, and this is going to be 0, 1. Okay? And I probably should have drawn that a little better there. There we go. Okay. So, let's determine it. Get that red marker again. Okay, so where's the R max value? Where's the largest R or the largest Y value between our two end behaviors? It's this guy, right? Okay, so here's how we can write it. At x equals -3, the relative max will be 3. Okay, and then for relative min, kind of the same thing. This is the lowest in between the end behaviors that we see it. So at x equals 0, the relative min will be 1. Okay? Talk about last second. Sorry about that for rushing at the end. Alrighty, another lesson done.